Okay, so let me introduce Daniele De Sensi from Sapienza University of Rome. Daniele is going to cover the part related to fundamentals on distributed memory systems from a programming model perspective, of course, so not topologies, for example. No. Daniele got his PhD at the University of Pisa with Professor Marco Danelutto. He spent 2 years and now almost at ETH, at SPCL Lab with Thorsten Effler, and his academic record is outstanding. So yeah, the stage is yours.
Thank you.
Thanks.
So this talk is gonna be about fundamentals, right? So let me start with the disclaimer. I know that there are people with a wide variety of background here, so this talk is directed to people that normally never programmed with MPI before or never been using a distributed memory system. So just to understand if that's actually the case, so how many of you already programmed with MPI or with any kind of distributed system, distributed memory system? Okay, half and half. So I'll try to say something interesting for both, but I mean, this is again basic distributed system talk. Okay, you will see something more advanced tomorrow, and in the afternoon you will see some tutorials on how to actually use this concept. But my task here is to prepare you so that you can understand what you're going to see next. Okay, so we are going to stay together for a couple of hours. So I will start with some motivation, challenges of using distributed memory systems. I will make a practical example involving collective operation, which is one of the most basic kernels that you will use if you have to deal with distributed memory. I will spend like 10-15 minutes by discussing a few research directions and what people are doing. So distributed memory system is a huge topic. Okay, so it's hard to say enough in 2 hours. So there will be many things that will not be covered, of course. But if you're interested in the topic and you would like to discuss, I will be happy to talk more about it offline. And then eventually I will draw some conclusions. So let's start with motivation. So why do we need distributed memory systems, right? So we have these GPUs that are getting faster and faster every year. Why do we need to use multi-GPU system, let's say, okay? And the reason is that the GPUs are getting faster, but there is a lot of pressure coming from application people, okay? So there are like every few months a new version of GPT comes out. It has large context and whatever, so there is always this pressure to build faster systems. And the only way that you can keep up with that is to build systems made of many nodes. Okay, so one single node is not enough anymore. So for doing any serious science, let's say, you at some point you will find a bottleneck. You will find, let's say, you will hit a wall and you will need to use more than one node. But let me explain this by showing you some data. Okay, so the first thing is the need for computational demand. Okay, so just one disclaimer. I talked about GPT, but this applies to many scientific domains. Okay, so I will just make examples with AI because now it's what everyone is talking about. But the same applies for chemistry, material science, physics, whatever. Okay, so the compute power you have, it's never enough. So I think that some of you might have already seen this picture. So we have on the x-axis the year, okay, till 2021. And on the y-axis, we have, let's say, the amount of computational power that you need to train some of these big models. There are language models, there are transformers, there are several things. And as you can see here, the computational requirement of these models increased by like 700 times every 2 years, or like 10 times every 2 years. And this is just too much, okay? Moore's law, so I think you have seen this already in the previous days. Moore's law, which is an empirical law, it says that basically the speed of a CPU or a circuit increases by a factor of 2 every 2 years. So there is this huge gap, okay? So one single chip is not gonna be enough to keep up with the rate of increasing computational power demand. And the same is also true for memory. Okay, so memory, if you take this model, they are using more and more parameters, even if right now there is a trend in trying to limit that somewhat. Okay, and again, the amount of memory that you need is going to increase 200 times every 2 years, but the actual memory that you can put on a single node is going to increase by 2 times every 2 years. So there is this huge gap between single node capability and what we actually need for doing science. And that's why you need to use distributed memory systems. Okay, as I was mentioning before, this applies to several other domains. I put some references there in case anyone want to know more about that, but this is true for climate science. I mean, for example, with climate science, why do you need more power? Because you basically model the surface of the Earth as a grid, and you try to make this grid with higher and higher resolution. Okay, so you try to model effects not on a 10-kilometer square, but like on a 1 kilometer square. And for that, you need a huge amount of computing power. Okay, so how do we keep up with that? The first option is what is called scale up or vertical scaling, which is the one that doesn't work. We already said that, which means that you just buy bigger GPUs, bigger CPUs, larger memory, but that's not only going to help in a limited way. So of course you cannot wait for a faster GPU to come out because you will waste money. So there are companies doing business with that. So if you just wait for a couple of years, you will be out of the market. So that's not an option. And as I was mentioning before, there is this gap between how much computing power you need and how much computer power you can buy. Have you seen this picture before? No? Okay, well, that's a quite popular picture. Again, we have on the x-axis the year, on the y-axis we have several things. Okay, so we have the frequency of the CPU. Okay, and as you can see, at some point this just stopped increasing, and this is for physical reason. I am not the most suited person to explain why this happened, but there are physical reasons why the clock frequency of circuits it's not increasing anymore. Okay, so at this point, people realized that we will never build a 20 gigahertz processor, so they started putting more cores in a CPU. Okay, so and here we have the number of cores that you have, and you can see that basically when this stopped, this started to increase. People started putting more cores. So this is why you are seeing like OpenMP and other ways of like doing multi-core programming. Okay. So that's the reason why you need to do multi-core programming. As I was mentioning, Moore law it's an empirical law that says that the power of a CPU increases by more or less 2x every 2 years, and this is just measured by the transistor count. So CPUs get more transistor rather than like having a higher frequency right now, and these transistors are mostly used for having more cores. Okay. But again, this is not gonna. I mean, like we can just build big node up to a certain point. Okay, we cannot keep like squeezing stuff into a single chip. At some point, you need to use distributed system. Okay, so the second option that we have, and this is what I'm gonna talk today, it's to scale out, or what is also called horizontal scaling, which means that you take one node, you take thousands of them, you connect them together, and in some way they will work and help solving your problem. Okay, so you usually have one server. Okay, they are made this way, so they're like this flat. They're called blade. Okay, you put many of them one on top of the other in a rack. Okay, so a rack is just one. I mean, it's something like this actually. So you just put a lot of servers there. You put a network switch, and you connect these servers together. And then you take one of these racks, you do copy paste, and you have like hundreds of them. And you build what is called a supercomputer. Okay, so that's basically it. It's just a bunch of multiple interconnected racks. Each rack is a bunch of multiple interconnected nodes. Now, supercomputer, like cloud companies, AI companies call it data center. Okay, so what's the difference right now? So is there any difference between supercomputers and data centers? So up to a few years ago, that was the case. So they used totally different technology, totally different business models. Right now, the technological gap, it's not there anymore. So, I mean, Supercomputers and data center now they look pretty similar. Okay, so if you run your MPI application on Leonardo, or if you run your MPI application on Google Cloud, on the expensive instances, let's say, you won't see much difference in terms of performance. Okay, because eventually they use the same type of GPUs, the same type of network. I mean, not Google Cloud, but let's say Microsoft uses the same type of network as Leonardo, and so on and so forth. So nowadays, this distinction it's not so huge anymore. There are some advantages. So okay, I do not work for cloud companies, so I'm not trying to convince you to buy AWS credits. So it's just like my I'm just trying to to give you a perspective. So what's the advantage of running things on a data center, for example? That you always have access to the newest hardware. Okay, so if you consider a supercomputer developed by a supercomputing center, that usually has a lifespan of a few years. So before they move to the next one, I mean, it's gonna be like 4 or 5 years. I don't know. On Azure, you will always get the last GPU available. Okay, so it's much easier to get access to the newest and fastest hardware that you can get on the cloud rather than on a supercomputer center. Okay, but of course it's gonna cost more. So there are a lot of trade-offs between cost and performance, which are not so easy. So there is not one thing that is better than the other, but it's important that you are aware of that. So as researcher, or as like public university researcher, it's probably going to be cheaper to run your stuff on Chineka or on any other supercomputing center, just because usually they give out compute hours to public institutions, right? But anyway, so the advantage of that is it's flexible. You can add as many servers as you want, and this keeps getting bigger and bigger. We will see that, of course, there are limits to that, but there is some overhead. Okay, now you do not have all your data on one single node, and you just access the main memory. So now you have data scattered across multiple nodes. You need to go through the network to access this data, and this has an overhead. And there are, of course, a lot of additional challenges. Some node might fail, a rack can crash, a switch might explode. So there are a lot of nasty things that can happen. So you have seen some of those nasty things on single node on Monday, I think, or it was yesterday, about like these radiations and stuff. Think about how much this can get worse when you have thousands of circuits in one data set. Okay? So the probability that something will fail is very high. So just think about that. So if you have one single node, if you have one single GPU, and that GPU will fail every 2 years, if you have, let's say, 200 more GPUs, the frequency of the failures will get much higher. Okay, so every few minutes, one component will fail. So you need to write your code or your infrastructure in such a way that it can deal with all those failures. If you want to know more about this thing about difference between data center and supercomputers, and especially from a network point of view, I suggest reading that paper. It's really nice. It gives you some more detail about the network infrastructure of those two different types of large scale computing systems. Okay. Questions so far? Okay, so I will move on and discuss a few challenges. So I say that there is some overhead in managing distributed computing systems. Why is that? And I will show you that with an example. Okay? So let's say some kind of distributed memory, hello world. So it's a distributed scalar sum. So you have a bunch of nodes. So these are servers. This is their memory, and they have some scalar in the memory. Okay, and they want to compute the sum between all those values. Okay. How do they do that? Let's see a very trivial way of doing that. So we assume that these nodes are connected in some way. Okay, I'm not going to assume any specific way, but I will assume that any node can send and receive data from any other node in the system. Okay, so what's a very simple way of doing that? So at the first step, I just have, so basically I say everyone will send their data to one node. That node will compute the sum, and then will send the sum to all the other nodes. So that's a very simple way of doing that. It's not a good way of doing that, but it's simple enough to explain. So they will send the data, it will compute the sum, and it will send the sum back to the other nodes. So now let me make a note here. Okay, so how this node actually sends data to this node here from a programming model perspective, let's say. It depends. Okay, so one of the most widely used way to do that is by using MPI that you will see in the update. So, and MPI works by doing send and receives. So you have some data, you send the data to another node, that node receives the data, it sends the data back to another node, and so on and so on. That's not the only way of doing that. Okay, so there are other programming models for which, for example, you assume to have a global shared memory. Okay, so you see everything as a big blob of memory, regardless of where this is allocated, and you just do load and store as you would do with the shared memory system. Okay, that again, that depends on the programming model you use. We don't care too much at this stage, okay, because eventually, even if you assume to have one global shared memory, eventually this data needs to move. And what I'm gonna show in this lecture is how the data moves and what is the cost of moving this data, regardless of how you actually program it. Okay, even if you program as a shared memory system, eventually the data needs to go around, and this is a case. Okay, so what's happened here? Let's focus on these two nodes. So N1 sends some data to N0. So how that actually works? So what's N0? So that's a server. Okay, so this server has some stuff inside. Okay, usually we put a CPU, we put a GPU or a TPU or any other kind of accelerator. We have disks, we have a main memory, and we have a network interface card. So that's the stuff that more or less you put on a blade. Then you have the other node, which is, sorry, you have your data in your memory. You have the other node that has its data in its memory. Now they need to talk and send this data. Okay. And this guy here, the network interface card, which will take care of taking the data from this memory and push it to the other memory. Now there are a few overheads here. So it would send the data there. I don't see anything. So okay, it will send the data there. It will. The animation is broken. Never mind. So, but just imagine that this piece of data goes here. It computes the sum and it writes the sum back into memory. Okay. So the first overhead is actually the time that you need to spend for wrapping this data into a network packet, send this packet to the NIC. The NIC will wrap the packet again with other headers and stuff, and then send it over the network. So there is a part of overhead which is happening here. Okay, so here the CPU, the memory, and the NIC, they are connected with a PCI Express bus or whatever, and you have to cross this bus multiple times, and this is cost. Okay, so this is just time that you are wasting. And that you were not wasting on a single node. Okay, so in the single node, you were just loading and storing data to the memory, computing stuff. Okay, now you have some additional overhead here. Data needs to move also to the NIC. That's the first type of overhead. And the second overhead is actually the data transmission over the net, right? So here there will be a copper cable or an optical fiber, whatever, but the electricity or the optical signal needs to move across that wire. And that's as a cost, okay, which again was not present for a single node. Okay, so we have these two types of overhead. So let's see why this is, I mean, what type of issues we have. So let's say that we have a node. So the node has this CPU or a GPU and the network interface card. And we have many of them. We have n nodes, each one has its own CPU and GPU. Now, time, I will show some kind of timing diagram. Okay, so time flows from left to right. Okay, so typically you start your application. So how does it work in the general case? So there are many ways of doing distributed memory application. The most simple and widely used way is that you have some data, you split the data across all these nodes, and each node will compute something on a part of the data. And then at some point they communicate and they update the data and so on and so forth. So that's a very standard way of doing it, like very generic way. Okay, it really depends on the application. Okay, so the CPU or the GPU will compute, and then at some point they need to exchange data with someone else. Okay, to update the results or to get some information that they don't have locally. So they will do some communication, okay? And this communication will happen on the NIC. So the NIC will encapsulate the packets, send that over the network, and so on and so forth. And you keep doing this in several phases. So you alternate computation phase with communication phases, and this goes over and over. Now, what's the issue here? The issue here is that we are wasting a lot of time and resources there. Okay, so here, while the NIC is communicating, the GPU doesn't have nothing to do. Okay, so you're just burning money. So these GPUs are super expensive. They cost like $10,000 each or something. And you don't want them just to sit there idle, waiting for data coming from the network. This is just money that you are throwing in the bin. So all the effort, let's say, it's made in trying to make this gap here as small as possible. Okay, so you would like to have you paid your GPU a lot of money, you would like them to work 100% of the time. If they are waiting, I mean, it's not. Imagine, I mean, like Meta announced a few weeks ago that they're going to build a cluster with, I think, 100,000 GPUs or something like that. Imagine the cost of that. And now you have those GPUs just waiting for them. That's bad. So all the effort is done in reducing that gap. So there are, and of course, I mean, this is not only relevant for the companies, let's say, also for you as a user. So when you apply for a grant and you require, I don't know, 1,000 compute hours, you don't want to burn half of the hours just having your GPU doing it. Okay, so your job, okay, as a distributed memory application developer, is trying to avoid something like that. There are a couple of ways, traditional ways in which you can do that. The first one is to try to have some overlap between computation and communication. So what you try to do, instead of waiting till the last moment to send the data, you try to anticipate that a little bit before. So this truly depends on the application. You cannot always do that. But if you really analyze your application logic, sometimes you might realize that you can anticipate a little bit the moment when you transmit the data. And while the data is moving, maybe you will start computing something else for the next step or whatever. So try to do that. Okay, so I don't have a golden rule on how to do that. This is truly application dependent, but try to see if you can anticipate the time where you send or receive the data in such a way that you can try to overlap this a little bit too. Okay, but that's the ideal case. Okay, that's still this is still like a very nice world where everything works properly, everyone is well aligned. When I do the communication, I will magically find the data there. Everything is like perfectly spaced, and that's fine. That's not always the case. Okay, what happens in general is that you have load unbalance. So it means that some cores might be faster, some cores might be slower because of unbalancing the data, for example. So you partition your data, but maybe some data is more complex to process compared to other data, and which means that some GPU will be faster than other one. It might be also because of manufacturing defects. So even if you buy two GPUs which are exactly the same, they will not have exactly the same runtime for the same kernel. Okay, because different physical reasons. So in practice, what you will have is that someone will finish earlier, someone will finish later. What happens is that for many applications, what determines the runtime is the slowest node. And that's bad. I mean, like this is called like the straggler problem. You will find many papers about that, especially now with deep learning. This is a huge problem because deep learning training works in this kind of tightly coupled and very synchronous process, for which you cannot just start the next training iteration if the next training epoch if the previous one didn't finish. Which means that if there is one single node out of 10,000 which is late, all the other ones are just waiting and you are wasting time. Now, again, I forgot to put the reference here, but there is a very nice survey in the case of deep learning explaining how to try to avoid that. So there are techniques in which you try to avoid being stuck because of one single node. But that's, again, it's really domain dependent. You might do that, or this might not work for your application. It really depends. But anyway, load balance is bad. Why? Because some of these some of this communication time, it's actually overhead. Sometimes it's just waiting. Okay, not even the NIC is working. I mean, no one is working there. They're just waiting for data to arrive. So um, try to keep your computation balance. Okay, measure it. Try to do some profiling, and let's see if, I mean, what your GPUs are actually doing. Whether they're waiting for something. I mean, this is a complex process, but it's something that if you're gonna work in this field, you should eventually learn how to do. Now, things are gonna get worse. Okay, so technologically speaking, this is not something that's gonna disappear with the new technology or whatever. Why? So if we see how fast the network gets year after year and how fast the GPUs get year after year, you can see that GPUs get a lot faster because of a lot of technological innovation, the way the architecture works. It's really, it really enables this kind of speed ups here. Like in this case, in 6 year, the GPU power increased by 26x. Okay, I don't have the updated data. It's up to 2020. The network moves at a much slower pace. So in 6 year, you're not going to have a 26x improvement. You're going to have maybe a 4x, 8x improvement if this is, let's say, the best case. So what do you have here is that if you consider this picture, um, the computation will get much smaller, but the communication will also decrease, but not as much. So this part of overhead here, which is not overlapped, is going to increase. So you're going to waste more money. And this is why many companies, I mean, you will see tomorrow a talk from NVIDIA, many companies are trying to find new ways for avoiding that problem. Okay. And this is an actual issue. So I already put some data here. I will not going to discuss each of these bars individually, but these are just a bunch of deep learning models. And here the picture shows the communication and the part that you actually are able to overlap. So this means that all this time here, this is not overlapped, and the GPU is just waiting. And that's again, that's bad. Anyway, there are many papers showing this effect. Okay, I just wanted to put some there. Now, this causes several issues. I'll try to explain one of those. So, did you hear about Amdahl's law? Okay, so let me try, since I've seen someone doing no, let me try briefly to explain how this works. Okay, so Amdahl laws, it's like a law or an equation to estimate the speed up of an application when running on n processes, threads, nodes, whatever. Okay, so S is the speed up, and you want to know how faster your application gets if you run it on 10 nodes rather than one node, for example. So if the speed up is 10, you are happy. Okay, so you buy 10 nodes, you get 10 times faster. That's the ideal case. In general, that's not the case. Okay, why? So this is estimated with this small formula. So what does this formula say? So this P here is a fraction of the application that can be made parallel. Okay, so now you start from sequential code and you try to parallelize it. You try to have different nodes executing different parts of it. But usually you cannot parallelize 100% of your code. So there is some part which is intrinsically sequential, and it's always going to be sequential, regardless of how many nodes you buy. For example, I/O. So if you need to read something from the disk, that's usually something that you do sequentially. I mean, you can do in parallel, of course, but this, again, depends on the application. So there are parts of the code which cannot be parallelized. And that's this 1 minus P. Okay, 1 minus P is what's the percentage of my code that I cannot parallelize. Okay, now there is this very nice formula. So what does this formula mean? Okay, so I show here on the plot the number of processors on the x-axis and the speed up on the y-axis. And this formula says that the smaller is P, the sooner I will stop scaling. Okay, so this is my performance. Let's say that, for example, my parallel fraction is 90%. which means that 10% of my code cannot be parallelized. So I start adding more nodes. I arrive here at 1,000 nodes. After that, the application doesn't scale anymore. So I can add 10,000 nodes, nothing's gonna change, okay? If this fraction gets smaller, like 75%, which means that 25% of my code cannot be parallelized, that's gonna stop even earlier, like after 128 nodes. So that's a huge problem, which means that you cannot just keep scaling and buying more and more nodes. At some point, this will stop. Okay, you will not get any benefit. Just one little note. Actually, Amdahl's law is quite optimistic. Okay, things in practice are even worse than that. So there is another law, which is Gustafsson law, which is a little bit more accurate and shows that things are even worse than that. Now, why I'm showing you that? Because this network overhead, actually, it's one of these non-parallelizable parts of your code. Okay, so that each node needs to send some data. There is no way that you can parallelize that or get it faster. Actually, that overhead gets larger and larger when you increase the number of nodes. It doesn't even stay the same, okay? It's getting bigger. So the network overhead on 2 nodes is much smaller than the network overhead on 1,000 nodes. Which means that you have to be careful also for that, because eventually you will stop scaling. Okay, so let me a little bit wrap up this this first part. Okay, so we showed that the computational demands grow at a much faster rate than the hardware capabilities. Okay, so we need to buy and use multiple nodes. If you want to keep up, we need to do horizontal scaling. So just go on distributed memory. And this memory, this application basically just communicates using the network. Okay, they send data back and forth between nodes. And there are two main overheads. The one is interaction with the NIC or the operating system on the single node, just to wrap this data and send it out. And the other one is the actual transmission over the network. And these two overheads limit the scalability that you can get. Okay? And try to avoid unbalancing your workload. So, any questions so far? Okay. So, I'm going to go a little bit more in detail into some of these concepts. Okay, so the first overhead we talked about is about the interaction with the operating system and the network interface card. Okay, so let's say that you do this with TCP. So TCP, you have to open a socket, connect the socket, and so on and so forth. Okay, so that's a huge overhead. You need to copy the data between the host memory and the operating system, like internal buffers. Then the operating system copies this back on the memory on the network interface card. Many data copies, huge overhead. The interaction with the operating system itself, it's also an issue. Okay, so you will get interrupt. You will need to do context switches. That's also another source of overhead. And in general, like the TCP/IP software stack is cumbersome. Okay, it was designed for the internet, I don't know, 50 years ago, or even more. It's for networks that maybe, I mean, I don't know what was the speed of the networks like in 1960, but I guess it's like matter of kilobit per second or something. Now we are like at 1.6 terabit per second. I mean, it's just like several order of magnitude more. So something designed 60 years ago, it's not going to work today. I mean, not as we want. And that's why several years ago, actually, several decades ago, people started studying and proposing RDMA. Okay, so what's RDMA? So RDMA is not Radio Disney Music Award. It's remote direct memory access. Okay, and the DMA. So each of these words has a meaning. It's there for a reason. So remote means that you are accessing something remote, so on another node, and you do a DMA. So you access seamlessly remote memory as if it was, let's say, local memory. Okay, more or less, this is the concept. Now, RDMA, it's a huge topic again. I'm just gonna, I mean, it's important that you know that it exists, and I will show you the intuition on how this works, but it's a huge topic, and I mean, it requires further discussion. Now, for some of you that already know what RDMA is, So RDMA, it's a concept, okay? So it's a set of theoretical principles that are not tied to any specific technology. Okay, so right now, the main provider of RDMA technology is NVIDIA. Okay, but there is not a one-to-one map. Okay, RDMA is a general concept, and any company or any researcher can implement its own RDMA system. So just don't get confused between RDMA, InfiniBand, or NVIDIA. That are different. I mean, it's just one instance of RDMA. Okay, the InfiniBand protocol. Okay, and again, this is not TCP plus socket. Okay, they just put TCP in the bin and they design something from scratch to be more efficient and fast. Okay, so what do you typically have? So it's based on two ideas. The first one is user space networking. So usually you have your application, you have your network stack that lives in the kernel, like your TCP IP stack, and then you have your network controller. And the first idea is, okay, let's remove the interaction with the operating system. Okay, if you look at the TCP stack, it's, I don't know, thousands and thousands of lines of code to manage every kind of strange protocol, every legacy device that you might have in your system, like it must have to be compatible with everything that has ever been designed, so it's a mess. And so they said, okay, let's just get rid of it. Okay, so and they split this network stack. They put a part of the network stack in user space and the part of the network stack on the NIC. Okay, so RDMA NIC are not just, I mean, RDMA doesn't just work with any NIC. You need an RDMA NIC. Okay. As a side note, actually, you can get RDMA to work on any NIC with a software solution, but this is just like emulation. It's not a proper RDMA NIC. Okay. So you need to have some special hardware there. So this part of processing is separated into these two parts, and the interaction with the operating system basically just happens once at the beginning. So you set up your communication when the application starts, but then all the subsequent send and receive and transmissions, they do not cross the operating system anymore. Okay, they just jump directly to the NIC, and that's quite a huge improvement in terms of performance. Okay, and that's what I just said. Okay, the other idea is just you bypass the kernel, and then you just don't interact with the kernel anymore. You just do it once or a few times at the beginning, and then everything is managed by the NIC. Now, the details of how this works are quite complicated. You can, I mean, if you want, I can give you references. I don't think I put those in the slides, but there are papers and tutorials and video on YouTube, whatever, of people explaining how this actually works in practice. But it's important that you know that it exists, and that's the technology that most supercomputers use in order to get fast and efficient networking. Okay, so what we can expect from that eventually? Okay, so what's the performance of that compared to TCP? So this is also some quite old data. It's from 2015. I think this paper was from Microsoft. So Microsoft at some point deployed RDMA in their data center, and so there are a few advantages. So the bandwidth it's much higher, especially for small messages. Okay, if you have a large, we will see this later. Okay, but usually when you have very large data to transfer, I mean, everything will work, and you will get nice performance. When you have small data, the network will make a huge difference. And then here, like if you have to send a 4 kilobyte packet, you get several a big performance improvement. The latency will also improve. Okay, so again here, TCP, RDMA gets much shorter. And the last advantage, which is also a very important one, is that since you are not, since most of this network management is moved on the network interface card, okay, it's not done anymore at the user level and neither in the kernel, the CPU occupancy gets lower. Okay, so before you had to do a lot of processing for like opening sockets, managing sockets, the assembled TCP packets, all a lot of crazy things that TCP does. Now all this stuff, most of this stuff is done in the NIC. So the CPU is free, which means that now you can use that CPU for doing something more useful than processing network packets. Again, CPUs have a cost. If you have a system with thousands of them, if you can save some CPU cycles and use those cycles for doing something else, it's usually better. So that's also another big advantage of RDMA, that CPU usage gets lower and you can use those cores for doing your actual application logic. Now, so this is, I just want to convince you that RDMA is the way to go. This is a picture showing the fastest 500 supercomputers in the world in June 2010. So this is the top 500 list. And the area of each of these supercomputers represents its computational power. So this system here, it's much faster than this system here, for example. Now, if we see how many systems use RDMA, it's basically this part here. So all these systems use RDMA or some variation on top of it. These systems here, they were using Ethernet, okay? So traditional software stack. This was in 2010. Now let's move forward to 2023. Basically, all of them are using RDMA. Okay, so there are just some old and small supercomputers that are still using Ethernet or something like that, but most supercomputers nowadays use RDMA. This is also true for like cloud providers. Okay, so this is why I was telling you that right now there is not much difference between a supercomputer and the data center. So until a few years ago, data centers were relying on TCP/IP. Okay, so they had the need to serve external users. Okay, and you cannot talk RDMA with an external user because he or she might not have an RDMA need. So they were anyway had to use TCP for communicating with the outside world. That's still the case, but now they can run RDMA internally. So like all these big cloud providers, they have some form of it. So like, for example, Microsoft is using InfiniBand. AWS developed its own RDMA protocol. So there are different solutions. Okay, some of them rely on existing technology. Some of them it's inventing new technology. But all of them also use RDMA. Okay, so that was the first overhead. Interaction with the operating system, with the NIC and whatnot, and we improved that by using RDMA. The second overhead is the network transmission. So as we said, we need to send some data on this link here. Okay, so we said that this might be a copper link, a copper cable, an optical cable, or whatever. Now, there are different delays that come into play when you send actually the data over the network. The first one is the transmission delay. So the transmission delay is the time that the NIC takes to push each bit over the link. Okay, so it pushes one bit at a time, and that's gonna take some time. So the longer the data that you need to transfer, the more transmission delay does it take. Okay, because it's just done one bit at a time. Then you have the propagation delay. The propagation delay is the actual time that one bit takes from here to here. Okay, so if this is a copper cable, this will be the time for the electrical signal to travel across this copper cable from the source to the end. If this is an optical cable, this is the time, this will travel at the speed of light, and this is the time that the light takes from going from here to here. So that's just something that we have no ways to improve. Okay, so that the upper bound is the speed of light. We can get faster than that. So that's going to be the propagation delay is going to be constrained. Okay, of course this also depends on the length of that cable, and there are many people trying to design large systems with short cables. Okay, so that's a huge topic about topology design. And it's a quite interesting one. But eventually, for a fixed cable length, you have an upper bound. Now, how these nodes are generally connected. Okay, so now if you have two nodes, you connect them with one cable. If you have 4 nodes, you need to find a way so that each node can talk to any other node. Now, there are different ways of doing that. Let's say that there are 4 nodes, you can just attach cables between all the pairs. And that's cool. That's okay. What if it's 1,000 nodes? Okay, that's not going to be possible anymore. Okay, so each node has a fixed number of network ports. Okay, it's a number of network interfaces. So how to do that? So usually in that case, you put network switches. Okay, so a network switch is just, I mean, the same that you have in your home. Okay, so it's just with blinking lights, and then you attach your computer there, your PS4 or whatever. It's just that network switches in data centers are much bigger and cost much more. Okay, and they typically have 64 ports, 128, 256, usually no more than that. Okay? Which means that you can attach like 128 nodes to one switch. Okay, so in this way, you have 128 nodes that can communicate between them. So if this one wants to communicate with this one, we'll send the data here. This will internally be forwarded here and then to the last node. Now, what if you have more nodes than the number of ports that you have on a switch? And here is where the fun part starts. Okay, so this is the issue of topology design. So how to connect all these nodes. I'm going to show an example, okay? But usually what you have is that you will have many switches, and then you try to connect in some way. And that's going to have a huge impact on the performance that you will get from your system. Okay, I don't remember what I wanted to say here. Okay, so this was the example I showed you before. Okay, so we say if we want to sum the numbers, everyone sends to n0, and then 0 does the sum. What's the issue with that is that now here there is only one link. Everyone is trying to send to n0. So here the data will wait. Okay, so they cannot all send to this guy at the same time. So here there is just one cable, and we are trying to push data from 3 cables into one. I mean, this is very layman terms, okay, and it's not like actual technical terms, which means that eventually these nodes need to wait. Okay, so the data will get enqueued here. So here there will be a queue, and packets will sit in the queue and wait for the other packets to go on and on. And this is the last type of delay. It's queuing delay, okay, which means that data will sit in a queue and needs to wait for the data in front of the queue to be pushed out, and then eventually the data will also be pushed out. So 3 types of delay. Again, there is not much, I mean, let me talk this from a user perspective, okay? There is not much that the user can do to improve that, and not even to improve that. So this depends on the speed of your network interface card. Okay, if you buy a 100 gigabits per second NIC, that's what you get. There is something that the user can do to improve queuing delay. Okay, I will just show you an example later, but that's the only thing that you can do basically. Okay, I need to connect my laptop to the power plug. If you are a system designer, you can try to improve propagation delay. Okay, but from a user perspective, there is not much you can do. Okay, let me stress more about this issue of network topology. So let's say that we have 6 nodes, okay, and we have switches with 4 ports. Okay, so how do we connect them? So that will be a trivial way of doing that. Yeah, you just put 2 of them, and then you use 1 port to connect these 2 switches. Okay. So again, as an application developer, this is not something that you do, but I want to show what's the impact of that on the performance of your application. So let's say that the network looks like that. Now let's say that node 0 wants to communicate with node 4, and node 2 wants to communicate with node 5. Okay, that's where the issue starts, because now you will have 2 different connections crossing the same link, which means that these 2 now will interfere between each other. So if here it has a network interface at 100 gigabit, it's actually not going to be able to push data at more than 50 gigabit. Okay, so the bandwidth of this link here is going to be split between these 2 users. Now, of course, if I had allocated the gray job on these 2 nodes and the orange job here, this would not have happened. Okay, so if this gray guy is here, they will communicate like this. 100 gigabits. This will be used only by the yellow one, 100 gigabits. So that's just to explain you that the way in which your application is allocated on the computing node has an impact on the performance that you see. Okay. So be aware of that. So if you run your job multiple times and you observe different network performance, one of the reasons might be because of that. Sometimes you get lucky and you get all the nodes which are close together in the cluster. Sometimes you get unlucky and they are scattered all over. Can you control that? To some extent. Okay, so Slurm has some flags that you can use to ask for a more, let's say, compact allocation. But this depends on whether this has been enabled by the supercomputing center or not. Slurm has also some flag to specifically ask which nodes do you want to use. So if you know how these nodes are connected, you can ask Slurm, look, I want to use node 0, 1, and 2. Okay. Now, you are on a shared system, and other people might have required the same. So usually specifying the nodes will increase your queuing time. So you know how supercomputers works, right? You ask for an allocation of X nodes, and then you wait. When those X nodes become available, you run it. If you start specifying constraints, queuing time will increase. You will have to wait more. But if you really want a controlled, let's say, controlled environment, you might want to allocate all your nodes under the same switch. Okay, usually you will see less performance variability. Okay, so this is just to know that this is going to have an impact. And this is the only thing that with which you can really play to try to reduce the overhead for the actual network transmission. Yes. Yeah, exactly. So this is the case. This is not the case for Leonardo, as far as I know, but in some system you have each node has multiple network interface cards, and those interfaces are connected to different switches. So that's called multi-ray. Okay, it's also a way to have redundancy. But again, the thing is that usually what you have is that each GPU is attached to one NIC and thus to one switch. So that GPU will go through that way deterministic. Some systems might also have something like you suggested. So basically, one GPU can send on can go out on two different directions, and that could be used, for example, to try to balance traffic. But that's not very common. So, okay, other questions? Okay, so let me make a practical example. Okay, so this is just the theory and why do we have this overhead? Now, what are collective operations? Collective operations, I think you will see this in the afternoon. They are common and basic computational kernels, let's say, to do some common operation on a distributed memory system. Like you need to sum, I mean, the scalar sum I showed you before, that's a collective operation. Okay, so you have each node having a number and you want to compute the sum. That's a typical thing that you want to do. Broadcast. So broadcast is another common case. So you have one node having some data, and the node wants to send this data to all the other nodes. Okay, so rather than implementing this manually, you call a function call which is called broadcast, and it takes care of it. And MPI has several of these, which you can use to do any kind of this kind of common operations. And why do I want to talk with that? Because I would like to show you how to actually model the overhead that you have on the network on your application. Okay, so you have an application, you know how the application communicates. Maybe, so let's say that you are developing your application and you have a few different alternatives to do the same thing, which is like semantically correct. Let's say you get the correct result, but there are different ways in which you communicate. Okay, you can have hey sending the data to B and then to C, or you can have a different communication. So how do you understand what's the best thing to do in that case? Okay, so all of them are semantically equivalent. It's just that they do different network communications. And I will show you an example. Okay, so I'll show you what's a cost model is. So a cost model is usually a simple function that tries to estimate the runtime of an application or of a system. Okay, so I have, in this case, I have that my runtime depends on S and N. So what are these two variables? So S is the number of steps I perform. Okay, so usually I need to do some distributed memory calculation. I do this in step by step. Okay, usually I do S step. After this S step, I have the result I want. And N is the number of bytes that I need to send. Okay, so those are the two variables. Now, each step has a cost that we call alpha. Okay, alpha is just imagine this as the network overhead we discussed before. So the time that you need to interact with your NIC or the operating system and ask the NIC or the operating system to transmit the data. So that's a constant overhead, which does not depend. So it does not depend on the number of bytes that you send. If you send 1 byte, you have an overhead of alpha. If you send 1 gigabyte, you still have an overhead of alpha. Okay, it's just a setup time, which is independent from the message. And n is the number of bytes. Beta is just the inverse of your network bandwidth. So if you have 100 gigabit per second NIC, beta is 1 divided by 1 bit divided by 100 gigabit per second. So that's the cost of how much does it take to push 1 bit over the network. Okay, so by doing that, you can model whatever you want. Okay, so you have your application, you model this that way with these two parameters. Now, these are models. Okay, so they're not, if this is gonna tell you 100 seconds, just don't trust it. Okay, it's just a way to compare different things. Okay, we do not care about the absolute value of that function. We care about whether this function for some specific value of S, alpha, N, and beta, it's smaller or bigger than another one. Okay. It doesn't tell you the actual run. Now, what's the first observation that we can get from this model? Okay, so this is called the alpha beta model. It's one of the simplest models that you can use to model network communication. Okay, so the first observation we have is that sending n divided by 2 bytes and then n divided by 2 bytes is different than sending n bytes all at once. Okay, why? Because here this will be, I have the blackboard. So in the first case, it will be, let's say, S is equal to 1. Okay, so it will be alpha plus n divided by 2 beta plus alpha plus n divided by 2 beta. Okay, and this is just 2 alpha plus n beta. Okay, so if you send all the n bytes as 1 at once, you just have alpha plus n beta. Okay, so this is just a trivial example, but it just tells you that it's better to try to coalesce your data transmission as much as you can. Okay, so it's sending 1 kilobyte followed by 1 kilobyte is not the same as sending 2 kilobytes. Okay, the first is much more expensive. So whenever you need to transmit data on the network, try to group those data transmission as much as you can and just do one big data transmission if you can. Okay, so this alpha beta model is just one of the possible models that you can use to model network transmissions. There are more precise one, let's say like the log P model, log GP model, and so on and so forth, that model other overheads, like they explicitly model a little bit more in details what's going on. Now, which one you should use? I mean, this is just a matter of what you need them for, and it's also a philosophical question. There are people that say that model must be very generic, and there are people that try to model every single overhead in the system. I personally like alpha beta because it's quite easy and usually it's good enough for what I need it for. But that might not be the case. Okay, so just be aware. Again, as I was mentioning, distributed system computing, it's a huge topic, so I'm trying to give you some references here and there in case you're interested in some of those topics. Just be aware that there are more precise models out there if you need to model things in a better way. Okay, so let's see this cost model thing with an example. Okay, so let's say that we have p nodes, and we need to do a broadcast. Okay, so it means that we have some data here, and eventually we need this data to be in all the nodes memory. Okay, so after the broadcast, we want these n bytes to be here, 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 and here. So one simple way will be that just n0 will do first ascent to n1, then ascent to n2, and so on and so on. And that's a quite trivial way of doing that. Another way of doing that is what is called a chain. So each node will send the data to the node on the right. Okay? So n0 will send the data to n1, n1 will send the data to n2, to n3, and so on and so forth. Okay? And eventually, all the nodes have the same data. How many steps did we perform? P. Okay? So the first step, n0 sends to n1. Second step, n1 sends to n2, and so on and so forth. Actually, it's p minus 1. After p minus 1 steps, everyone has the data. Okay, so that's, remember, in the cost model, we have this parameter s. In this case, s is equal to p minus 1. How much data did we transmit at each step? N bytes. Okay, so the data is on n bytes. At the first step, I don't need to touch the TV anymore. So at the first step, n0 sends n bytes to n1, and so on and so forth. So we have p minus 1 step. Each step has a cost of alpha. At each step, all the n bytes are sent, and we have this cost per byte of beta. So we model this, and eventually we get this formula. Okay, it tells us that the time required to complete this collective operation is p minus 1 times alpha plus n beta. So we do p minus 1 step. At each step, we need to pay the setup overhead to set up the communication, and we need to transmit 10 bytes. Okay, can we do something better? Okay, so this is where the fun starts. So you need, semantically, what you need to do, it's clear. You have some data in one node, and eventually the data needs to be in all the nodes. Can we do something better? Of course we can, and this is possible, for example, by using a tree. So instead of doing this linear chain of processes, you arrange them in a tree, and you do a broadcast. Okay, so you have n0 sends the data to n1. Then what happens is that at the next step, n0 will send the data to n3, and then 1 will send the data to n2. Okay, so now the data is on 4 nodes. Now at the next step, all these 4 nodes will send something. And you have that n2 will send to n4, n1 will send to n5, n3 will send to n6, and then 0 will send to n7. So it's just a tree. This is a special tree. It's just a common tree, which is called a binomial tree. So how many steps do we perform here? 3. Okay. It's logarithmic in the number of nodes. So before we had a number of steps which was linear in the number of nodes. Here it's logarithmic. How much data do we send? Exactly the same as before. Okay, so we still send the same amount of data. It's just that now we do fewer steps. So what's the intuition here? Like at a little bit at a higher level. So when you do a chain, after n0 sends to n1, it will not do anything anymore. Okay, so n0 sends to n1, and then it's done. Okay, you will just wait. Here we basically try to have at each step all the nodes that have some data will send that data to someone else. Okay, just the best thing to do. Okay, and okay, so we have logarithmic number of steps, and at each step all the n bytes of send. So we have log 2p times alpha plus n beta. So okay, before this is log p, that was p minus 1, this is always beta. Okay, that was an easy one. Now, there are better ways of doing that. This depends on many things. This depends on what the actual value of p is, what the actual value of n is, what alpha and beta are. But I mean, people have been studying these kind of problems for decades. Okay, so you will find many, many papers on collective operations, and once in a while someone comes out with a new algorithm. It's not that common anymore. This is an old problem, so, but once in a while there is something new coming out. Okay. Okay, this one is the best one. Let's see a little bit more complex thing. Okay, so here the answer was clear. Okay, it was log p, it's smaller than p minus 1, it's fine. It's not that, that's not always the case. Okay, so I will not show you the algorithms, but I will just show you the models. Okay, so trust me that these are real models of algorithms which are used in practice. I will show you the models for two algorithms for doing the all reduce. The all reduce is another collective operation which is widely used in scientific computing, deep learning. It's like really one of the basic building blocks of distributed computing. Okay, so we have an algorithm A which does a logarithmic number of steps. So the cost model is log 2p alpha plus log 2p and beta. So that's the first algorithm. The second algorithm does 2 log p steps plus 2 n beta. Okay. Now, which one is the better? Okay. So now we have one algorithm which does less steps but sends also more data than the other one. So which one would you use? It depends on the other values, right? So in this case, it's not so easy to answer. It depends on how large is alpha, on how large is beta, on how large is p. It depends on the variables. In general, for this specific case, we would use this algorithm when n is small. No, we'll use this algorithm when n is small, and this algorithm when n is large. Why? Because when n is small, the time is dominated by this first part here. Okay, so if n is small, this becomes negligible, and everything is dominated by the first part. When n is large, this part dominates it, and this part is negligible. This, of course, also depends on the number of nodes and on many other things. But this is just to show you that for doing exactly the same thing, exactly the same operation, which in this case is just the sum, the distributed sum between vectors, there can be different ways of doing that. And it's not always clear which one is the best one. And this is the same for any distributed algorithm that you can implement. So this is why I'm talking to you about cost models. So when you design your distributed algorithm, try to reason with pen and paper whether you're doing the best thing you can do, or if maybe you can do something better. Okay, so to summarize, there can be multiple algorithms implementing the same distributed operation. I think I have a slide later for that. Okay. This algorithm, as I was mentioning, have been well studied for years. So if you need to do any of these operations, start implementing your algorithm from scratch. 90% of the time, it's not a good idea. So just use libraries which have all these implementations and usually can select the best one for you. Unless you are really an expert and you know what you're doing, don't try to implement a broadcast by doing send and receive binary. Okay, so that's usually gonna fail. It's not a good way. We can model this algorithm in terms of number of steps and bytes transferred, and the best algorithm usually depends on the number of nodes and the size of the transfer. Okay, I don't have the picture here. So which other factors play a role? So we just say that we have this n and beta, alpha, and so on and so forth. This also depends a lot on the network topology that you have. But that's going to be more complicated to model. Okay, if you want, I can talk about that offline. But usually, the best algorithm also depends on how your nodes are connected, in the sense that the way in which the nodes communicate determines how many bytes goes over each link over the network. And this has an impact. It's not easy to model. It's not easy to understand. I just want to mention that that's just part of the story. Okay, there is another part that most people neglect, but it's as much as important as this. Okay, so how do you actually run a collective? Let's say that you have your, I don't know, biochemistry application, you have your vectors of floating point numbers, and at some point you need to do a sum between those vectors. Okay, so there is MPI. You're going to see this in the afternoon. I think they are also going to show you collectives. Tomorrow collectives. Oh, tomorrow, yeah. Today is GPU tutorials. Okay. Tomorrow you will see MPI. There are a bunch of libraries. Then there is UCC. So UCC is a big effort for also having a library to do collective operations. There is Nickel by NVIDIA. Okay, so this is particularly targeting GPUs. So when you have to do collectives with GPUs, you can use Nickel. That's quite well optimized. AMD has its own library as well that with much fantasy they call Recall. And there are many others. Okay, Microsoft has its own. I mean, these are popping up like mushrooms. Why? Because right now with this deep learning frenzy, I mean, collective operations is like a very basic building blocks of all distributed training. If you see like this FSTP by Meta or any kind of model, at some point to train, they need to do the collectives. And so this is why everyone is doing research on that right now. Okay, so I will not discuss about this picture. So this is just about how all these things interact. So these are just layers, okay, of things built one on top of the other. So it's not easy to understand how they interact, but it's just to know that they exist. Now, how to select the collective algorithms? Okay, so we have seen that there are these two algorithms for doing the reduce. How do you can you pick it? So usually the library does that for yourself. Okay, so the libraries like MPI are supposed to be optimized in such a way that they pick the optimal algorithm depending on how many nodes you're using and how many bytes you're transferring. Those are heuristics. Okay, so they might not always pick the best algorithm. Sometimes if you play and try to tune it, you can get better performance. Okay, so be aware that if you profile your code and you see that you're spending a lot of time in a collective operation, one thing you can try is to try to force MPI to use a different algorithm. Okay, so sometimes this works. And like some libraries, like for example, Nickel and Recall, they are quite advanced. Okay, so they can also detect, so MPI doesn't do that, but Nickel and Recall, they detect the GPU they are running on. They know exactly how much is the bandwidth between those two GPUs, and they optimize a lot. So they determine using heuristics how many bytes do you have to keep in flight and a lot of other things. So especially for GPUs, using Nickel or Recall sometimes gives better performance than MPI. So be aware of that. If you have a multi-GPU application, try to run your collective with Nickel rather than MPI and see if anything changes. Okay? So how do I decide whether to use MPI or Nickel? That's not easy. Okay, so we have no general rules for that. Just try and see what happens. And I will show you a picture here. So this is the number of GPUs, and this is the message size. And I mean, I don't care about the number. So the number means that if it's greater than 1, MPI is better than Nickel, and if it's smaller than 1, Nickel is better than MPI, or vice versa. I don't remember. But anyway, it's important to know that for when it's greater than 1, one is better than the other. When it's smaller than 1, it's the other way around. And as you can see here, it depends. Okay, it depends on the message size. It depends on the GPUs. So be sure that you're using the best framework for the type of communication you are performing. Okay, so really there is no general rule here. So this is very much engineering and like hammering things down and try things and see if they work. But it's important that you are aware of that. Not all the collective libraries give you the same performance. Now, this is more or less what I wanted to say about distributed system. I'll just spend a few minutes talking about research directions. Okay, and even here, people are trying different things. I mean, I'm just going to talk about 2 or 3 things here, just to give you an idea on how things are evolving right now. And so I will talk a little bit about in-network computing, about compressed collectives, multi-GPU computing, and automatic synthesis of collective operations. So these are just 4 topics that I will just briefly touch. I think I'll be done like in 10 minutes or something. But of course, as I was mentioning, there are many, many other research directions out there. So in network computing, what that is? I see you smiling. I know that you know that. Okay, so in network computing, you have nodes. These nodes are connected with a switch. And so far, like until a few years ago, the NIC was doing the NIC. So it was just getting packets and pushing out. And the switch was doing the switch. Okay, the switch was taking packets from one port and forwarding it to another port. And that was it. So then people said, okay, why they just need to do just that? Okay, can't they just help us and compute something as well? And so they started to put logic into the NIC. So now you can buy smart NICs. Okay, smart NICs are NICs that have some ARM cores or any other kind of cores where you can install your operating system and run some stuff on the NIC. Why is that? I mean, there are a few reasons for that. The first one is that you keep your CPU free, so your CPU can work on something else. The other reason is that you don't need to copy data from the NIC to the main memory or and then to the CPU register and so on and so forth. So you save some latency. You process data directly on the NIC rather than moving the data around. And there are a few other reasons. And this works. Okay, so you can go and buy them and use them. There are some from NVIDIA. AMD has also some smart NICs, and then there are a bunch of other startups that are also building those. And if you want to know more about that, tomorrow there will be a talk by NVIDIA exactly on that. I mean, they will also cover that. Okay, there will be a talk by Salvatore and Gil. I suggest you attending because they're going to give you much more details about that. And they also put here some references in case you want to know more about the scientific aspect of it. So that's one thing about in network computing. The other thing, at some point people said, okay, why don't we just also process data on the switch? Why is that? I will show you that with an example. It makes sense in a very few cases. Okay, so it's not. I mean, you're not going to run matrix multiplication on a switch. Okay, that's going to be just nonsense. But for some type of processing, it makes sense to run it there. So let me give you some historical information. How this start? I mean, how this began. People working on internet services and stuff. You design a protocol, and that protocol is there. Okay, it's standardized. The protocol has this header. This many bits are used for IP address and so on and so forth. And now people said, okay, but we don't want to wait 15 years to design a new protocol and just wait for that. So they wanted to basically modify the packet structure in such a way that they could implement any custom protocol. Okay, so it really began like people working with internet services saying, okay, I don't want to be tied too much to the protocol. I want to have the freedom to tune and change the protocol as I want, to add the custom header because maybe I need this header. So one typical example is telemetry. Okay, so you send the packets from A to B, and you want to know how much time did you spend on each switch on the path. Okay, how do you do that? Each switch will add, I don't know, 4 bytes by saying, okay, the packet was here for 20 microseconds. Okay, so and eventually the network operator knows what happened in the network. And then people started to hack that and start doing a lot of crazy things. I will show you one of the most useful way in which you can use it. So can you buy smart switches? Yes, let's say. Okay, so the main vendor was Intel up to last year. Then it died. I mean, Intel didn't die. Okay, it's the branch that was making the smart switch that died. Okay, it was called Tofino, and that was the most used one in academia. Yes, P4 exactly. Yeah, and you program it with the very nasty language which is called P4. And programming this device, it's worse than programming an FPGA. Okay, it's like the worst thing that you can try in your life. I spent 1 year of my life doing that. I don't want to do it anymore. Okay, so Every time that people say, "Oh, I got a nice idea on Tofino," no, and it's dead anyway. So it's why? Because now on the NIC, it's kind of reasonable to have a processor, right? The NIC manages, I don't know, 100 gigabits per second, and that's something that you can still somewhat deal with the general purpose core. The switches has 64 ports. Each port has 100 gigabits. It's a lot of data. You cannot just put an ARM core there and manage all those packets. It's not gonna work. So they have. So I'm just doing this big digression, but anyway, we have time. They have this kind of ASIC, which is basically a pipeline. Okay, it's just a bunch of compute units. You have a block here, then you have another block here, and so on and so forth. The packet will go through this pipeline, and in each stage you can only do a fixed amount of operations, and that's super complicated. I mean, it means that you cannot have loops. Okay, you might have them with some nasty tricks, but it's gonna drop performance. You cannot do many things that you would do normally with the computing architecture, so it's very limited. It works in some cases, but again, it's something that has some potential. It's quite limited, and to be honest, in the HPC world, I'm not sure what they can be used for. I mean, I will show you one use case which is very clear to me, and I'm sure that this works, but I'm not sure for what else they can be used. So let me show this example. So you have a network. Okay, you have a network. These are the switches. These are the hosts, and this is the data. Okay, it's just a vector. And you want to do again all reduce. Okay, which means that eventually you want these nodes here to have the sum between these vectors. We said before that we had some algorithms for doing that, blah, blah, blah. So why the switches can help us with that? Okay, so the first thing you will do is to say, okay, I have these nodes. I will build what is called a reduction tree. So it's a tree that has as a root one of the switches, and as the leaves all the nodes that participate into the reduction. Okay? So just build this kind of logical tree. So you don't have someone going there and like removing cables. Okay, so this is just the logical view. The cables are still there. It's just that we are not going to use them. Okay, so what do? You send the data up on this tree. So this switch receives A1 and A2 and does the sum. The same here and so on and so on. And you do this level after level. Here, again, it does the sum. Eventually, the data reaches the root, and you have the total sum. And then here is the easy part. You just send the data down, and eventually all the nodes get the fully reduced data. Okay. Just imagine again, let me repeat this. You have nodes. Each node is a vector. You want to sum those vectors. So you build a tree where the leaves are the nodes, and the root is one switch. You have one pass when you go up. So the data goes up and gets aggregated level by level. When it reaches here, you have the total sum. And here, you send the data back down, and eventually this data reaches all the nodes. Okay, so it's just a tree for summing data from the leaves. Why this is useful? Okay, it has been shown both practically and theoretically that this can improve the performance by a factor of 2. Okay, which is quite a huge performance gain. Why? Because it basically goes from 2 alpha to alpha. Okay? So sorry, from 2. So if you don't do that, the optimal algorithm will be 2 times alpha, 2 times p alpha plus n beta. Okay. So if I didn't do this wrong, this should be the best algorithm that you can have when you're not doing that. When you're doing that, this 2 disappears. Okay? So you get the 2x performance. So this is a use case that works, and this is something that exists. Okay, so NVIDIA have switches that does that. Okay, it's called SHARP. It's not with this kind of pipeline architecture. It's a different ASIC that has been designed for doing that. What else can we do beyond that? I don't know. I mean, to be honest, I thought about it for quite a long time. I'm not sure that in HPC we can use these smart switches for anything more than that. Okay, so I think they are very useful for people doing services, internet, and stuff like. But for the actual compute part, I don't know. Yeah. For most collectives, this can be used. Okay. So even if you have to do a broadcast, you could send the data up and then ask the root to broadcast the data down. But beyond collectives, I'm not sure. So if someone has an answer to that question, I'll be happy to discuss, because I didn't still figure it out what they can be used for. But SmartNICs, they are useful for many other things. Okay, so SmartNICs, they have quite a few use cases. Okay, so this was about in-network computing. Compressed collectives. So I'll just have one slide on that. So what's the idea now? That you do collectives, and at some point you need to send these n bytes. Okay, can I compress the data? Okay, what if instead of sending my entire buffer, I compress it, I transmit less bytes, and then I decompress it? This is a quite reasonable idea. Whether it works or not depends on many things. So you can have lossy compression or lossless compression. People usually don't do lossless compression. Why? Because it's costly. So the time that you spend in compressing your data, it's much higher than the time that you save by sending less data. Okay, so it's a trade-off. So you compress if you can compress it faster than the time that you save, like by transmitting less data. So usually you do lossy compression, and there are a few ways of doing that. Of course, it depends a lot on the application, right? Because then it means that your application will work not on the, let's say, on the original data it was supposed to work, but on some approximated data. So some application can tolerate it, some one not. How to compress it? One typical way is to do quantization. So you have like 32 bits floating point elements, you compress it to 16 bits, 8 bits, or whatever. You lose some precision. That's acceptable in some cases, it's not acceptable in others. Like weather simulation, all this kind of stuff, not cool. Okay, so they want to work with 64-bit numbers. Machine learning, good. Okay, so machine learning, you can quantize like you want. So there are models that work with 1 bit. So instead of sending 32 bits, you send 1 bit, and magically everything works. But this depends a lot on the model, on the application. It's something that, again, you need to try and see what happens. It might destroy all your data, or it might work fine. The other approach is sparsification. Okay, so you have a vector of 100 elements. You just select, I don't know, the 50 biggest elements, and you drop the other one. Again, whether it works or not, it depends. Okay, so just try and see if that can be reasonable. And then there are other approaches like that are using neither quantization or sparsification. You can find the references there. What else? Multi-GPU computing. Okay, so now why this is, I forgot to put a slide about that, so let me draw. Okay, let me show you my amazing drawing skills. So why that introduces new challenges. So now you have a node, and let's say that you have 4 GPU. Okay, here 1 GPU, 2 GPU, and then you have another node, and you also have 4 GPUs here. So now these GPUs are connected in some way. And then these nodes are connected. So what's the issue with that? Is that usually this one here, let's say this is 800 gigabit per second. Okay, these are not make-up numbers. So this, if I remember correctly, these are the numbers from Leonardo. Okay, so these are actual numbers. So this link here, it's a 800 per second link. So this link here, it's a 100 gigabit per second link. So there is 1 order of magnitude difference there. So as long as you communicate between GPUs on the same node, it's very fast. As soon as you go out, bad. So what's the impact on application developers? You must be aware of that. If you can do most of your communications within the node between the GPUs, it's better. Okay. What's the impact of that on collectives? It's hard, right? So we model this with alpha and beta, but now we have two different alpha. We have the alpha for this and the alpha for this, and we have the beta for this and the beta for this. And this is not so clear on how we can do good things with that. I mean, the algorithms that we have, they work well enough in these scenarios. Are the best algorithms that we can have? No. Okay. So it's an open problem. It's something that that people are studying. You as an application developer, bear in mind that if you have your application, you have 12 processes, try to understand which processes are running here and try to map them in such a way that most of the communication happen between those processes. Okay, so originally, until before multi-GPU nodes, whether you are communicating between node 0 and 1 or between node 0 and 2 was kind of the same. Okay. Now it's not anymore, because if 0 is here, 1 is here, and 2 is here, okay, if you communicate here, it's different if you communicate here. So just check that you are allocating your nodes properly. I think that tomorrow we will see some of that. And if you want to know more, also tomorrow there will be the talk by Dida Munat, which will talk a little bit about multi-GPUs. I'm not sure she will cover collectives, but you will see other issues that you have with multi-GPU systems. And the last point, which is kind of related to this one, is automatic synthesis of collective algorithms. Okay, so I just say that it's hard to understand what's the best way to exploit this kind of heterogeneity in the bandwidth. So there are people that, I mean, when you don't know how to do a thing, what do? You just throw machine learning at it, okay, and you hope that it will solve the problem for you. That's quite typical. So there are people that try to apply machine learning or other optimization techniques to determine what's the best algorithm to run on these kind of systems. Okay, so this is a picture from Lumi. This is the Finnish supercomputer, and it has 8 GPUs per node. And as you can see, some GPUs are connected with 1 link, some with 4 links, and so on and so forth. So it's crazy to understand what's the best way to exploit all this bandwidth. Or you can have something like that. I mean, it's all kind of different crazy topologies. So some people have this kind of automated generation of algorithms. They work, but the generation itself takes a very, very long time. Okay, these are hard optimization problems, like they use this kind of simplex algorithm and so on and so forth. So it's and we don't know whether those algorithms are the optimal ones or not. Okay, so the optimization process comes up with an algorithm. It works reasonably well, but we don't have at the moment, at least for the projects we have, any way to determine if this is optimal. So let me conclude. So distributed memory is unavoidable in some domains. Okay, there are problems that requires you to go on multiple nodes, and there is no way out of that. So the sooner you face it, the sooner you try to address that, and the better it is. Be careful with this kind of overheads that you have in network communications. Be aware of those, and be aware of tricks that you can use to overcome some of those overheads. Try to also understand how your application communicates. Okay, so try to see if that's the best way to do it, or whether you can do something better. It's a dynamic and hot research area. I just scratched a little bit the surface, but there are many issues that people are trying to solve, both from industry and from academia. Okay, so this is a topic which right now it's hot for everyone. If any of you is a student and want to do a master thesis or a bachelor thesis on that, drop me a message. And I also have open positions for interns, postdocs, or PhDs in case you want to work on these kind of topics. And that was my last slide, so I'll be happy to take any questions you have.
How does RDMA work with GPUs? Because I can imagine with CPU, it's from system memory to the NIC, it's easier than from the GPU memory.
So right now it works perfectly also with GPU. So they have this kind of GPU direct for which you can transfer data directly from GPU memory to NIC memory, and then the NIC will do RDMA. So it's something that works. I mean, it's It was not like that until a few years ago. I mean, until a few years ago, we had you had to do still to transfer the data manually. Okay, so you had to copy data from the GPU memory to the host memory and then do RDMA. Right now, the NIC is attached directly to the GPU. Okay, so right now, on those systems, uh, it's much easier to transfer data between GPUs than between CPUs. Just because the NIC is attached to the GPU rather than to the CPU.
So not from the PCI bus of the system, but directly from the GPU itself.
Exactly.
Okay.
So it doesn't. It's the path now from GPU to network. It's much faster than the path from CPU to network in most cases.
Thank you.
One more question, maybe more generic, regarding all the interconnection between the switches and all the nodes when we are in a supercomputer.
Yeah.
I was wondering if there is any kind of research or advanced topic regarding the interaction of the topology with the fact that the load of that topology depends also on the applications that are running. Well, we discussed the fact that one node can be connected to a different switch,
Yeah.
and the runtime that might be, the traffic and the delay and the cost over that might change. And it's not just our application, the one that we did, and also what the rest of the community running on the supercomputer is doing. So is the switch capable eventually to do a sort of fingerprinting or analysis of the traffic and optimize that to lower the cost of the transmission, or is this totally generic and kind of unpredictable topic?
Okay, so that's a good question, and it like covers an aspect that we didn't cover, that is routing. Okay, so eventually this packet needs to go somewhere. I mean, they need to go from point A or to point B, but there might be 5, 6 different paths from going from A to B. So supercomputers typically try to select the least congested path. So they try to estimate how many packets there are on each of these paths and to pick the least congested one. This is good on paper. In practice, it's something which is super hard to do because basically each switch just sees the next hop. So if the path is 5 hops long, it doesn't have any idea of what's happening next. They make some heuristic and guesses which work reasonably well, but not always. So I've worked a little bit on this area, and I have a couple of papers showing exactly that adaptive routing in practice, it's not that precise, right? What you can do at the application level to fix that? Again, there are some really dirty tricks and like that you can play to like, let's say, drive a little bit the routing algorithm in one way or another to influence a little bit the decisions, but there is no explicit control. Okay, so there are some ways to let's say, to bias things a little bit in the way he takes the decision, but it's not something really explicit. So eventually, from the application perspective, there is no way that you can control how packets are routed. I know that there are some companies which I cannot name that are like working in a way to give users also a little bit of access to that, but I'm not sure how much access and how this works exactly. But this is one of these problems where actually smart switches can become useful. But again, it's more a problem of traditional networking rather than computing, the computing part. Okay, it's like, for example, setting fields in a packet header to tell the router to pick a very specific path, or something like that. But again, it's a very limited control, usually. Does it answer to your question, or if I'm not sure I totally understood the question? It was perfect.
So if there are no other questions, let's thank again our speaker.